A warm welcome to all the viewers for the course Strength of Material, AME 302. And the most important thing is that today in this third lecture we are going to discuss about elongation of the bar. So strength of material, when we are talking about, in my previous lecture I have already explained you that what is the requirement of the strength of material, means why basically we are going for strength of material. From this particular course, we will be able to know the various properties of material that are used to perform the various designing of the product, as well as we need to know that how much it can resist the load, what is the stress, what is the strain involved on it, and so and so. So today's topic is elongation of the bar. As you can see that elongation of the bar, when it is coming, it obviously means that you are applying some sort of load over that particular object or over the particular job. And then you can see that what are the changes that are occurring over that particular material or the structure. Now, when you are implementing some sort of load, that particular material should have that resistance power to resist that particular load. And if it is unable to resist that particular load, then obviously it will get some break or it will get some failure. So as you can see that we are here discussing about the elongation of the bar. We are implementing the load. The load can be tensile, it can be compressive, and the most important thing is that after implementing the load, what are the changes that is occurring on that particular bar, we are going to have a look. So in this third lecture of strength of material of module 1, we are here going to discuss that what are the various changes that are occurring in that particular bar. Well, myself Thea Pal, Assistant Professor of Department of Mechanical Engineering, is going to discuss the topic today about elongation of the bar. So without any further delay, let's have a look at the content. So initially we are talking about the content. So first we will be starting with change in length due to axial loading. So after implementing the load, that is axial load, what are the changes that is occurring in this particular length of that particular bar? Next, in this particular module we are going to discuss elongation of a taper rod under the action of a coaxial load. So till this much we have seen that we are talking about the change in length for a cylindrical bar. Now if I take a taper rod, then what is the change in elongation that will be occurring? For taper rod, we are going to discuss in today's lecture. Next, there is the elongation of the bar under its own weight. So when you are using a bar and it has been hung freely, and then you are seeing that the bar has got its own weight, then what is the elongation of the bar that is occurring in that particular condition? So what I was telling, that there is a bar, it is hanging freely, but the bar has got some weight, and in that particular situation, how it is getting elongated or what is the change in elongation that is occurring, we are going to have a look at that particular portion. Next, we are talking about bar of varying section. Now the bar can be having a various section. What I basically mean to say is that somehow in the middle it is having a diameter of suppose 10 millimeter, and both the free end it is attached with the diameter of somewhere 5 millimeter, somewhere 4 millimeter. So you can see there are lots of various varying in the section, not only with the dimension, but it can be changed with material also. So don't think that a particular bar means of one consisting type of material. No, it can have different type of material too. So if I talk about the different type of material that is getting involved while calculating the various section of the bar, then I must say that we are going to use the term that is the compound bar. Compound bar means different material, it has got different texture, all are assembled together to get a desired product, that is one type of product, and then we are saying that what is the change in that particular bar with its initial weight. So that also we are going to calculate in this particular module. And finally we will be discussing some sort of numerical, that is how you are going to solve out numerical for all this particular condition, that is change in length due to axial loading, elongation of a bar, that is of taper rod under the action of a coaxial pull, and then we will be discussing about the elongation of a bar under its own weight, and finally we will be discussing about the compound bar with initial weight. So today in this particular lecture I am going to cover up the change in length due to axial load, and along with that we are going to discuss the elongation of a taper rod under the action of coaxial load. So this particular content will be explained in 3 different lectures. So in the first lecture of this particular content we are going to have a look on change in length due to axial load. Along with that we are going to talk about elongation of a tapered rod under the action of coaxial pull. So without any further delay, let's have a look at the content. So what I was telling, that we are going to discuss about change in length due to axial load. Axial load means the load that has been applied through the axis of that particular bar or the particular object. So if you consider any bar and just consider it that it is having its original length as L. So you are implementing the axial load at both the end. Now the load can be tensile, the load can be compressive. So what we think is that when we are implementing some tensile load, we are considering it as a positive load. Why? Because with the implementation of this tensile load, you can see that the object is getting elongated in length, but it is reducing in diameter. So you can see we are considering it as positive because you are implementing the object and you are giving a load on both the end and you are elongating that particular object. So as I have already told that first of all you consider a bar and you just consider small l as your original length. So after you are implementing the axial load, you can see certain changes in the length, and this length, it can be in increase also in length, it can be in decreased in length. So as I have already told, if you are going with a tensile load, then obviously there is some increase in length. But if you implement compressive load, then obviously there is a decrease in length. So you have to be very sure whether you are going with the increase in length or you are going with the decrease in length. If you are implementing tensile load, that means you are giving an increase in length, and if you are using compressive load, that means you are giving the compressive load. So when you are implementing some compressive load, though your length is getting decreased, but your diameter is getting increased. So that is not the factor, it will not help us in any way, it will not affect our calculation also. we have to know that whether we are implementing the tensile load or we are implementing the compressive load. But the thing is that we have to calculate the entire thing. That is how you are going to bring the change in length, or how you are going to calculate the change in length due to your axial load. So first of all, I have already told what you mean by stress. Stress means you are implementing some sort of load over some sort of particular area of that particular object. So I can say from there that stress is the ratio of implementing the load per unit area. So stress you can use as, what you can say stress, that is load per area, isn't it? Okay. Now we are talking about the strain. Strain is change in length to its original length. That means change in length if I consider as del L, and if I consider the original length as L, then strain is equal to del L by L. So you can see here this is del L by L. What is this? This is none other than change in length by your original length. Now if is represented as the stress set up in the bar due to the application of external load on the bar. So as I was telling that it can be represented by F or it can be represented by sigma. So stress is none other than, it is the stress that has been already set up in the bar due to the application of the external load over the bar. And next we are talking about E, that is Young's modulus, or so what I was talking about, this is none other than stress. Stress means it can be represented by F or it can be represented by sigma, and E is the Young's modulus of the material, of the bar material, or it is also known as modulus of elasticity. So E is basically representing Young's modulus or modulus of elasticity. So modulus of elasticity or Young's modulus, it is basically known as the ratio where stress is proportional to strain, or you can say sigma by small e. Sigma means stress, or it can be denoted by F, and E means your strain. So as I have told, Young's modulus or modulus of elasticity states that stress is proportional to strain within elastic limit. So from here if I get an equation, then can I write that, if you can see in this particular portion here, that is modulus of elasticity is stress by strain. It can be also written as strain is equal to stress by modulus of elasticity. Now this stress is what? This stress is basically what? You can write F is equal to P by A. F is equal to P by A, because this is your load per unit area, which is very commonly known as stress. So here in this particular equation, if you put the value for strain E, that is del L by L is equal to F by E, or del L, if you keep the del L here, just del L here, then you can also write that is F into L by E. F means stress into length by your modulus of elasticity or Young's modulus. Now this F can be also written as P by A. So what you did is that F is equal to P by A. P is what? P is your external load that is applied to the bar, and A is your original cross sectional area of the bar. So if I get the equation right now here, that is del L is equal to FL into E. This is the final equation. Del L is equal to FL by E. So if you know the value for F, that is the stress, that is P by A, then you can also write del L is equal to P into L by A into E. So finally, if you want to calculate the change in length due to axial of load, then you have to state that the equation is also written as load into length by area into modulus of elasticity. So whenever you are going to calculate the change in length for any sort of cylindrical bar having the axial load as P, then you can use del L is equal to P into L by A into E, which is very commonly known as load into length by area into modulus of elasticity. So now let's have a look at the next slide. So now we will be discussing about the elongation of a taper rod under the action of a coaxial load. So far we have already discussed about the elongation of the bar, but that was a cylindrical bar and that was a straight bar even also. But the load always that we have applied is always coaxial pull. Coaxial means the load is implemented through the cross section, or you can say through the axis of that particular object or of that particular taper round bar, or it can be anything. Coaxial means the load is always applied through the axis. So now if you consider this particular figure, and you can see that the taper bar is having the length as L, and you can see two load, that is the axial load P has been implemented at the extreme end of this two rod of this particular taper, and you can see that we have considered an elementary strip of a very small length, that is your dx, at a distance of x from the smaller end of this taper. So this small d is none other than smaller end of the taper rod, and your capital D is the larger diameter of the taper rod, and this is a taper object you can see, and P we have used the tensile load that has been applied to the rod at the very extreme end, and you can see the load has been applied at the axial position, axial or coaxial position of the taper rod. And what I have considered is that I have to take an elementary strip of a very small length that I have considered as dx, and I have considered it at a distance of x from the smaller diameter of the taper rod. Now how we are going to calculate the elongation of the taper rod? Let's have a look. So as I have told that your total length is L. The total length of your rod is now L. So if I ask you what is the increase in diameter, then you have to consider how to calculate the increase in diameter, that is capital D minus small d. Capital D is what? Your diameter of the taper on the larger side, and small d is the diameter of the taper rod on the smaller side. Now if I want to know that what is the increase in diameter with respect to the length x. As I have already told that I have considered a strip at a distance of x which I have considered as dx. So if I ask you what is the increase in diameter of the taper rod if it is having a length of x, obviously the value will be calculated capital D minus small d by L into x. So for x distance, what is the increase in diameter with respect to your length, it has been mentioned. Now if I ask you what is the diameter of the elementary strip, then you have to add small d plus capital D minus small d by L into x. So you have to remember this particular portion if you are wanting to calculate the diameter of the elementary strip. Then capital D minus small d by length L into x. With that you have to sum up the diameter of your smaller side of the taper bar. Now I would like to ask you that what is the cross sectional area of the rod at the location of a distance x from the smaller end. So now we are going to calculate, that is the value for cross sectional area of that particular strip at a distance of x. So cross sectional area always it has been determined by pi by 4 into d square. So already I have calculated the diameter of the elementary strip, that is d plus capital D minus small d by L into x. So you are aware of that diameter of the elementary strip. So if I ask you to calculate the area of the elementary strip, then you can say that pi by 4 into d square. So here you can see in this particular equation, that is pi by 4 into d plus capital D minus small d by L into x the whole square. So what you have got the value as pi by 4 into capital D plus, you can see this is d by L into x, and that has been given as square. So a n, you can see this n, this small n is none other than capital D minus small d by your length L. This has been termed as constant. Now we are going to calculate the elongation of the elementary strip of a length dx, because I have already shown you in the previous picture that this is the picture, this is the smaller taper end and this is the bigger taper end, and you need to initially find out the elongation for this particular strip, that is dx. And if you are able to calculate this elongation of this particular small strip, then you can calculate the entire one, because we have to just integrate it, that is from 0 to L for the total length. So let us have a look here. That only I have did, that is initially I am finding out the elementary elongation of the elementary strip at a length of dx, and it has been given by, again I am telling the same formula, that is change in length is none other than P into L by A into E. So P means that is the load that has been given, L means what is the distance you have considered. So for the elementary strip the distance has been considered as dx. So here it has been written as dx by area into E. So area is pi by 4, that I have already told, this 4 have been got here above. So pi into d plus nx the whole square into your elongation. So now we are going to integrate it. So you have got the change in length for what? Now elementary strip, it has been mentioned by a into p into dx by pi into d plus nx into E. So this is the formula that has been given for change in length due to coaxial pull in a taper rod and you have calculated the change in length for a particular elementary strip. But if you need to go for the entire taper rod, how to calculate the entire total elongation, then I must say this particular change in length has to be integrated with the length from 0 to L, because the taper bar initial length is what? 0, and the completed length is your L. So you have to integrate it, and that has been only done here. That is 4p into dx by pi into d plus nx whole square into e, and it has been integrated from 0 to L. And here you can see after integration you have got 4p by pi e, then you have integrated from 0 to L for dx by d plus nx whole square, and you can see 4p by pi e. It can be also written 0 to L integrating d plus nx minus dx. And after that, what you have done, after calculating the entire thing, the final value that you have received is 4p by pi ne into capital D minus small d by capital D into small d. And in this n particular, the small n value is known to you, that is capital D minus small d by your L. So if you put the value for capital D minus small d by L for n, you will get the final equation for del L, that is 4pl by pi e capital D and small d. So you can see that for elongation of a bar with the action of coaxial force, which is denoted by change in length is equal to P into L by A into E, but the same equation is not implemented for elongation of a taper rod under the action of coaxial pull. So if I have a look for the elongation of a taper rod under the action of coaxial pull, then the equation will be like this, that is del L is equal to 4 into P into L by pi into E into capital D into small d. So you can see the word change you have observed in this particular situation. Now let's solve a numerical of that particular elongation of the taper bar. Here in this numerical it has been told, that is you have to consider a circular bar taper. So this bar is taper and it has got a diameter of 10 centimeter to 8 centimeter. That means the lower end or the shorter end of the taper rod has been considered as 8 centimeter, and the larger diameter of the rod, it has been considered as 10 centimeter, and the length has been considered as 1 meter, or you can represent as in centimeter because other data have been given in centimeter. So 1 meter is equal to 100 centimeter. Okay. Now it has been asked to you that determine the elongation of the bar under a pull of 80 kilonewton. So your load that you are implementing is none other than 80 kilonewton, and it has been told you have to assume modulus of elasticity, that is E is equal to 200 kilonewton per millimeter. Okay, so 200 kilonewton per millimeter, it can be converted into centimeter, and that is 2 into 10 to the power 4 kilonewton per centimeter square you can write if you are multiplying with 100, and if you are multiplying with 100 to the power 4, then you can go with the kilonewton, but okay, no need, you just write 200 into 100 kilonewton per centimeter square. Okay, now it has been told that find out the diameter at the smaller end to limit the elongation of 0.04 centimeter under the same pull. So your elongation length has been already fixed, that is del L2 for that particular x, it has been given 0.04 centimeter. So if I consider this particular thing, that is if I say what is the increase in diameter for your 100 centimeter length, then your answer will be capital D minus small d. So capital D is how much? 10 centimeter. You can see capital D is your 10 centimeter and small d is your 8 centimeter. So from there you can get the increase in diameter, that is 10 minus 8, that is your 2 centimeter. Next, if I want to know what is the increase in diameter for x centimeter, this is the x centimeter, then same way this 2 by 100 your original length into x, the answer will be 0.02 x. Now if I ask you what is the diameter of the taper rod location where elementary strip has been considered. So you can see that for the small particular thing that the length will be, diameter will be 0.02 x. Along with that you have to summation the small d. If I ask you the cross section of that particular thing, then means pi by 4 into d plus this 0.02 x whole square. So you are able to calculate the area. If you are able to calculate the area, and if I ask you what is the elementary elongation of the strip, then same thing, that is P into your distance by area into your elongation, a modulus of elasticity, that is been given here 2 into 10 to the power 4. So you can see after calculating it, we have got the value, that is elongation in the elementary strip is 0.0824 centimeter. So this is your change in length, this is your change in length that we need to calculate. So finally we came to end of this particular lecture, where I have already told you that how basically the elongation is occurring due to your coaxial load for a particular bar or for taper bar. So you can see for both the section it has got different variation or different calculation to calculate the change in length due to the coaxial load that has been implemented over a particular cylindrical bar as well as for taper bar. So if you have liked the video, then please stay connected with my lecture, and in the next lecture we are going to discuss about how the change in length is basically calculated for the composite material, as well as if it is having a different variation in the various section, as well as we are going to discuss about suppose the rod or the bar, it is hanging in a free portion, it has got its own weight. So there is also a change in elongation also. So all these things will be discussed in my next lecture for elongation of the bar. So let's have a summarization that what we have discussed in today's lecture. It is none other than we have discussed, or we have taken a bar. Initially we have implemented the load, that is the coaxial load at both the end, and we have considered a load as tensile load itself. It can be taken as compressive also, it depends upon the demand of the numerical. So it can be compressive, it can be tensile, anything it can be, it depends upon the requirement. Whatever may be the load, tensile or compressive, it's nothing to do with the calculation. Only I have to consider that how the elongation is occurring. Whether the elongation is getting increased, obviously then you will get positive value. If it is having compressive load, that means the elongation is getting decreased, that means the negative value you will be getting. That means negative value in the sense not in that particular way, that is if your length is having 100, if you are increasing, if you are implementing the load, then for example it will increase by certain percentage, and then you can get the value for 100 to 110 millimeter of the elongation of the length of the bar. But if you are implementing the compressive load, that means there will be decrease in length from the original length. So this is what we are calculating for the elongation of the bar, which is basically represented by P into L by A into E. But for taper we are using some different concept because now the rod is not a symmetrical one, and neither you can say it is having the equal diameter from both end, because in case of taper, at the end, one end is having smaller diameter, other end is having a larger diameter. So in that particular respect, your calculation for change in length is also getting varied. So we have already solved some numerical for this particular type of content. So please stay connected with me. If you have liked the video, then please like it, subscribe it, and stay connected with my channel. Thank you so much for connecting with me. And in my next lecture, I am going to discuss about the elongation of the bar due to its own weight, as well as we are going to discuss about some sort of composite bar where we are going to implement the load also, where it has got its own weight also. Then what is the elongation or the changes that are occurring, everything will be discussed in my next lecture. Thank you once again.